Hi, this presentation addresses the final coursework proposed for our Digital Systems class, which consists of a microprogrammed architecture for a boundary scan test coprocessor. After watching this presentation, you shall be able to explain the objectives and functional specifications of the system that has been proposed for your coursework, and you should be able to set up a plan to begin your work. I would recommend you two main sources of complementary information. One is a paper that I have written myself with a previous Master of Science student at the college last year, and that has been published into the Circuits and Systems Journal in July 2014, and that paper is available at this address, and also a general book on microprogrammed state machine design, which has this ISBN. The final prototype may be represented as shown here. The boundary scan test code will have been loaded by the main processor into this dual access shared memory. In the case of our implementation, we can simply design this shared memory as a ROM, since we will not have a main processor. Our boundary scan test coprocessor will get the operation codes and the operands for the test program from the shared memory, and then while executing these test commands, it will issue the appropriate signals to TDI, TMS and TCK for the boundary scan board and collect the information arriving from TDO. We will of course assume that the shared memory has previously been filled with the test commands to be executed. So these are the minimum functional features of our test coprocessor. We should support at least one test access port. We should be able to run the test commands that were shown in the will be shown in the following slide. These test commands for the corresponding object code will have previously been loaded into a shared memory, and the whole thing will start to work upon an external start order, as we will see in a moment. So this is the list of test commands that must be supported by our test processor or coprocessor. With these commands, which are in fact identical to those that were used in the first part of our course, it will be possible to test any boundary scan board. Your main task indeed consists of designing the ASMV charts that detail the workflow of each of these test commands, as I will illustrate later using the multiple TCK command. What each of these commands does is summarized in this table. Now, the proposed test coprocessor is indeed a finite state machine with data path, and as such it can be represented by its data path and control path architectures as shown here. The data path is relatively simple and comprises two counters, these two counters here, one latch, one serializer, and one divider. The serializer is needed to convert the bytes loaded by from the shared memory into the bit stream driving the board TDI pin. Because the total number of bits to shift is not necessarily an integer multiple of 8, we will need to count how many groups of 8 bits are to be shifted. And this is the value that will be loaded into the integer word counter represented here on top. And the remaining bits to be shifted will be loaded into the remaining bits latch indicated in the data path as well. If we want to shift 23 bits into the board boundary scan chain, for example, that corresponds to 2 groups of 8 plus the remaining 7 bits loaded into the R-bits latch. Notice that dividing by 8 is simply allocating the bits in positions 7 to 3 to their new positions 5 to 0, and this can indeed be done by a combinational circuit, so there's no need for a real divider for this block. Then the R-bits latch simply receives the bits that were initially in positions 2 to 0. The C-bits counter, or current bits counter, is used to count the number of bits that are currently being shifted. In fact, it is more appropriate to say that it is used to count the number of test clock or TCK cycles needed to conclude the current operation, since in the case of the test command mTCK or multiple TCK, we are not shifting any bits but simply issuing TCK cycles. This slide also shows the inputs and outputs of the control path. The outputs are of course used to control the operation of the regular sequential circuits that are present in the data path, and the inputs represent the particular operating conditions of interest, such as reaching 0 in the current bits counter, or reaching 1 in this counter, and so on. Notice that the shared memory is needed both for the control path and also for the data path, since the current test opcode defines the sequence of control actions that will be sent to the counters and serializer, and also to the data path. The contents of the shared memory will also need to go to the data path on occasions, since the bits to be shifted, for example, are to be loaded directly to the serializer block. Finally, while the board TDI pin is driven from the serializer in the data path, the board TCK and TMS are driven directly from the control path. Now, the control path can in fact be designed according to 2 main approaches, and I'm referring to the control path block in the bottom here in this slide. One of them is the traditional finite state machine approach, as you already know. It can also be designed as a microprogrammed architecture where a read-only memory is used to store the sequence of control signals and next state information. So instead of designing the generation of this set of signals as a hardwired approach, we do it in the form of a read-only memory, in the content of a real read-only memory. Because we have used the FSM approach in the ABC player, what I propose here is that we do this now as a microprogrammed architecture. You can read chapter 4 of this book if you want to go into more detail on the operation of microprogrammed architectures, but I believe that the information that I will present to you in the following slides will be sufficient to learn what you need to know. Now, the control path architecture may be designed as in various forms, and the one shown here is just one of them. You can follow this solution or design one of your own. I have to say that I am not entirely sure that this solution will work, for the simple reason that I did not have the time to implement it. You really have no idea how much time I spent thinking about this solution and the time needed to create these slides. This solution is indeed a variant of the solution that you can find in the Circuits and Systems paper, referenced in the beginning. where the shared memory was a different type. It was in fact a FIFO in that paper. In order to limit the time taken by this presentation, I chose to explain the operation of this control path in the following video. What you need to do now is to design the ASMD chart detailing the sequence of operations that correspond to each test command. In this slide, I illustrate this process through the example of the MTCK, or multiple test clocks command. This command takes up 2 bytes in the shared memory, one for the command operation code, or command op code, which will be used to point to the microprogram memory section that contains the sequence of control signals and next state information for its implementation. And the other position in the shared memory will be taken to indicate the number of required TCK pulses. So the microprogram memory section that implements this test command therefore needs to increment the shared memory address, which takes place in the first state called MTCK_0, and then to load its content into the current bits counter. So the RAM content will go into the C bits counter, and this will define the number of TCK pulses that need to be generated. Then we need to decrement this counter until it gets to 0 and generate 1 TCK pulse for each decrement operation. And this will take place while we keep inside this loop of MTCK2 and MTCK6. When the content of the current bits counter reaches 1, there is only 1 test clock pulse left to be generated, and we can then move on to state MTCK3 to prepare the final phase of the execution of this test command. So after generating the final TCK pulse, we will need to increment the shared memory address in order to point to the next test command opcode. This opcode will be loaded into the control path bank register, and the ASMD state register, which defines the offset within each microprogram memory section, will be reset to prepare for the execution of the new test command. Well, in the very beginning, notice that when we start the test program execution for the first test command, as shown here on the left, we will need to drive an external start command, which in practice will come from the main processor. This start command must initialize the control path architecture by resetting the shared memory address and the control path itself. Once we have the ASMD chart, well, I recommend, of course, that you try to draw the ASMD chart for one of the TMS test commands, for example, in order to try to learn how this works. Once we have the ASMD chart for a given test command, it becomes relatively simple to fill in the content of the corresponding microprogram memory sector. To do this, you may use a table as shown here, which in this case was created using a Google spreadsheet that you have available in our Drive workspace of our course website. Notice that for each state, in this case MTCK_0 to MTCK_6, we need to specify what must happen in the control path. Under the comments column you see what happens in the control path, and also in the data path as well. The control path operations are indicated here in the micro operations column field, while the data path operations are indicated individually for each signal. IL to BK. IL is the load signal to the integer word counter, and so on to the SS, which is the shift serializer control signal. They are all indicated on the top right of this slide. BS and BK are the board TMS and board TCK test access port pins. Please take a moment to look into these operations and try to relate them to the architecture represented earlier in the control path slide. Now, that control path slide shows that the operations taking place in the control path architecture are defined through a block called encoder, which is a combinational circuit converting the external start order and also the micro operations defined by each ASMD state into the corresponding orders for the control path blocks. The function of each of these signals is indicated here in the bottom of this slide. And again, you should compare the information shown here with the control path architecture that was presented in the corresponding slide. And please recall that its detailed operation will be presented in a following presentation in order to avoid making this one too long. Finally, how shall you organize yourselves to carry out this work? I think that it will be beneficial to set up a list of shorter milestones and deliverables, one for each week, as shown here, instead of asking only for one final deliverable at the end. I defined the milestones and deliverables that I propose in this slide. But please realize that this does not mean that I am suggesting a purely sequential approach to the development of this coursework. In fact, you should split the tasks from day one and start with VHDL coding for the proposed data and control path architectures from the very beginning. At the same time, you can appoint who is in charge of each of these milestones and deliverables, and that is the person who must concentrate on delivering by the indicated deadlines. I suggest that you allocate the data path to one member of the group, the control path to another member, the ASMD charts to another member, and finally choose one member to work as project manager and be responsible for the final integration and delivery. Finally, thanks for your attention and good work.